Hello everyone and welcome to the second episode of Physics World Live. I'm Mateen Durrani, the editor of Physics World. It's great to have you here with us in our new online panel discussions, which we're bringing to you in partnership with the flagship IOP journal, Reports on Progress in Physics. We've got about 800 people registered for this event, and we're going to be talking about the future of particle physics to mark the 70th anniversary of CERN, which takes place next week. So I'm now going to hand over to our host for the event, Physics World News editor, Michael Banks. And by the way, we'll have plenty of time at the end for questions, so do send them in and we'll try and get to as many as possible. Over to you, Michael.
Thanks, Mateen. So hello, everyone. My name is Michael Banks and I am the news editor of Physics World magazine. So welcome to this second Physics World Live event, which is all about the future of particle physics. So I'm delighted today that we have three incredible particle physicists and speakers with us for this event. So to introduce our speakers briefly, we have Tulika Bose from the University of Wisconsin-Madison, Philip Burrows from the University of Oxford, and Tara Shears from the University of Liverpool. And before we get started in a moment, each of them will give a brief introduction of themselves. But before we do that, just a little bit about this event and what we will cover. Of course, particle physics is a huge area, and so unfortunately we can't cover everything in just 1 hour. So with that in mind, we will mostly focus on high energy physics. So in other words, the physics that's achieved at these kind of huge particle smashes, for example, CERN's Large Hadron Collider. So in the first half, we will examine the state of particle physics as it currently stands, looking back at some major milestones, such as the discovery of the Higgs boson at CERN's Large Hadron Collider in 2012, and then look at a little bit about the current status at this huge particle smasher, which is currently undergoing a major upgrade, and what that might achieve. Of course, CERN is celebrating its 70th anniversary this year, so kind of what better time than to look at its achievements and its aims for the future. Then in the second half, we will examine the possible future direction of particle physics, kind of looking where it's heading in the coming half century and what the next big particle collider might look like. So let's start off with some brief introductions then. Phil, would you like to start?
Okay, thank you very much, Michael. Well, hello, everybody. So my name is Philip Burrows. I'm a professor of physics at Oxford University, and I'm also the director of the John Adams Institute for Accelerator Science. So I'm slightly unusual in that I've spent roughly the first half of my career as a card-carrying particle physicist, but for the second half, I've been working mainly with the particle accelerators, which of course is one of the important enablers of the science that we do. Thank you.
Tulika, do you want to go next?
Sure. Hello, everybody. I'm Tulika Bose. I'm the Vilas Distinguished Achievement Professor of Physics at the University of Wisconsin-Madison, experimental particle physicist working on the CMS experiment at the LHC. I've served as its physics coordinator and trigger coordinator, and currently I'm overseeing software and computing for the US part of CMS. Recently, I served on the particle physics project prioritization panel, or P5 as it's called, within the US, that came up with a strategic plan for the future of particle physics in the US. So happy to talk to you today.
And last but certainly not least, Tara, do you want to go?
Hi, everybody. My name's Tara Shears, and I'm a professor of physics at the University of Liverpool. And I'm an experimental particle physicist working on the LHCb experiment at CERN's Large Hadron Collider. And I lead a group at Liverpool. We have responsibilities for building precise particle detectors for the experiment. We analyze the data. We look after computing. I've also just started my stint as the UK LHCb contact person. And in my spare time, I'm the Institute of Physics Vice President for Science and Innovation.
Perfect. Well, thank you for those introductions. So, okay, let's get going then. So maybe we could cast our minds back a decade or so to the actual discovery of the Higgs boson, which was in 2012 at CERN's Large Hadron Collider. So of course, the Higgs boson was predicted by the standard model of particle physics. So many physicists, as I understand, were confident that it existed and it was just a matter of finding it. I say just, of course, it was a experimental tour de force in particle physics at the LHC's huge Colossus, CMS and Atlas detectors. I wonder perhaps if we could start, maybe someone could kind of put that discovery in context and its importance to the history of particle physics, not small order. Maybe Tara, do you want to have a go at that one?
Okay, well, maybe if I say a few words about why the Higgs is just so important for particle physics, and then Tulika, do step in, because as a member of CMS, you are the absolute expert in its discovery. So the Higgs boson is a huge deal for us in particle physics. We've got 4 fundamental forces that we know about in the universe, and 2 of them, or at least the strengths of 2 of them, are intimately linked with the Higgs field, if I'm honest. And the Higgs field so not only explains to us the relative strengths of the what's called the weak force, the force that's responsible for the sun burning its fuel, and electromagnetism, but it's also the explanation that we've got in our theory for why particles, fundamental particles, have mass. We have no other way of explaining this within the mathematical framework that we understand the universe with. Now, the issue with the Higgs field is that you can't see it. You really can't see it. But what you can see is the Higgs boson, the particle that's associated with it. However, this particle is exceptionally difficult to see. It's quite massive, and that means you have to have a very high energy facility in order to momentarily create it, in order to see it. But it's also really, really rare. And that means you have to have a facility that has the power to create so much data that you then stand a chance of seeing it. And the Large Hadron Collider was the very first facility to unite both of those. Now, I can't underline enough just how big a deal the Higgs boson existing or not existing was at the start of the Large Hadron Collider. So Michael, you mentioned that we all expected to see it. Well, I've got to say, a few of us sort of hoped we weren't going to see it, because that would have just meant that the standard model, our theory of particle physics, which is just so good at predicting everything that we've measured so far, we know it can't be the whole story. And maybe this was going to be the part that didn't meet, the hole that appeared, the window to the unknown. And so I have to say, some of us that weren't involved in CMS and Atlas were, all ears, really interested in what was being found out, but also semi-rooting for some complete upset. But whatever happened, it was going to be absolutely massive. And if the Higgs boson wasn't there, there would really be trouble in our understanding. So I hope that gives you a flavour of just the vast importance of this particle to our whole understanding. But I'll let Tulika tell you about the immense challenges in actually finding the thing.
Right. Yes. So, July 4th, 2012, I think of it as one of those, historic watershed moments. We all know where we were that day when the discovery of the Higgs boson was announced. And it, of course, came about as a result of people in the CMS and Atlas collaborations just working for years, literally, trying to come up with different ways in which they could figure out if there was such a particle. And so it was kind of amazing when 2 experiments working independently, we could not share and discuss our results beforehand. Both then came up with that amazing discovery. So when it was announced at the seminar held at CERN, we really didn't know. I was in CMS. I knew what the CMS result was, and that we had found this particle with a certain mass and that it showed up in different analyses. But then to actually see the Atlas result come in, and there it was, exactly at the same place. That was quite amazing. Of course, the question then to all of us, and I sort of, resonate a little bit with what Tara said, is it the Higgs? And so, of course, what we could say at that point, that this was a particle that had properties that were consistent with the Higgs boson. But whether it was the standard model Higgs or a sister or a cousin or a brother of that Higgs, we didn't quite know. And in fact, in the last sort of 10 years or so, we've been working really, really hard to actually pin down, that is, measure its properties at a level where we can actually say definitively. And of course, we've come very close. So all we can say at this point is that, yes, it looks pretty much like the Higgs that was predicted by the Standard Model. However, there are so many questions that we still don't know. You know, it is a very unusual particle. It is a particle, only fundamental particle that has like a zero spin angular momentum, and it's unique in the way its properties are. And so whether it is a fundamental particle, like other fundamental particles, electrons, etc., we know, or is it a composite particle composed of something else? We don't know. Does it decay to something that's exotic? We don't know. How does it interact with all of the other particles in the Standard Model? While we've understood its interactions with some of these, there are still many more particles that we don't quite understand. And then, of course, there is a very big open question about how does the Higgs interact with itself? Does it? And if so, what is its interaction strength? And then so there are many, many exciting questions that we are currently trying to answer at the LHC.
Yeah, I mean, just to follow on Tara's point, I mean, is there a frustration in particle physics that the Standard Model is so successful? I mean, we've just had, I think it was a couple of weeks ago, we had a new measurement on the W mass, I believe, which again aligned perfectly with Standard Model predictions. Of course, we know there are cracks in the Standard Model. It doesn't predict certain things, but you know, it seems like it's not letting up at all. Like, you know, it seems like everything seems to be aligned with the Standard Model. I mean, what's your kind of impression on that?
I can start with that. So what I can say is, I think the fact that we haven't seen anything sort of exotic that has been not predicted yet tells us that we kind of need to be looking at a different energy scale. That's one possibility, that, you know, we just need to go much higher in energy. The other alternative is that, you know, we've been looking in the standard places. Maybe there are particles that couple so very lightly, feebly with Standard Model that we haven't yet been able to see them. And so for that, we need loads more data, which we are expecting to get firstly at the high luminosity LHC and then other colliders in the future. So I just think, given the open questions, right, there are lots of open questions about why does matter dominate in the universe. I mean, we had equal amounts of matter and antimatter at the very start of the Big Bang, and then somehow we are existing, we are matter, and where has all the antimatter gone? What about gravity? You know, this is one of the 4 fundamental forces, and we do not have an explanation for gravity in the Standard Model. So these are 2 of the, you know, big open questions. And then the third, which is that the universe as we know it, all of the particles, they comprise what I would call the visible part of the universe. There is a part of it that we call dark, in the sense that we can't really see it. We can only infer its presence, for example, through the gravitational interactions. So what's responsible for that? So the fact that we still don't know the answers to these questions tells us that the Standard Model absolutely needs to be extended. And we therefore need to look for this new phenomena. We just need to look for it in perhaps at higher energy or in non-standard ways.
Okay, yeah, I mean, you mentioned the high luminosity upgrade then to the LHC. So I mean, that's what's kind of happening at the moment. It's a £1 billion, dollars, however you want to look at it, upgrade, which is certainly a lot of money. I mean, sometimes, you know, scientific facilities themselves cost that amount of money, never mind an upgrade to it. So what, you know, why do we need the high luminosity LHC, and what are kind of physicists expecting that it might actually produce? I don't know, Phil, do you want to have a go at that one?
Yeah, maybe I could start us off, Michael. I mean, let's start off with the wonderful machine that we have, the LHC. I mean, it is truly an extraordinary machine by any standard, and as a particle collider, it is completely beyond equal anywhere else in the world. And so, just to explain briefly, you know, there are lots of little bunches of protons that are circulating around the 27-kilometer circumference of the ring. So there are roughly 100 billion protons in each of these bunches, and there are 3,000 bunches going one way, and there are 3,000 bunches going the other way. And then at these 4 magic places around the ring, the bunches are brought into collision. And so the measure of the performance of the accelerator is conventionally given in terms of something called luminosity, or flux in old-fashioned language, and it's the number of particles that cross at these collision points per square centimeter per second. And that number is roughly 10 to the power 34 with the Large Hadron Collider as we have it today. And if you think about that for a minute, physicists, we're used to quoting big numbers, 10 to the 34. Just think about how many particles per square centimeter per second that really is, and it's utterly phenomenal. And so that's delivered a huge amount of data that the experiments, chewing on and looking for all sorts of new physics and so on in that vast data sample. But with the high luminosity upgrade, we're talking about making roughly an order of magnitude increase in the total data sample that will be collected over the next decade or so. So in other words, roughly, we've only got 10% or so of the total data sample in the bag up to the end of the LHC running. And then after the upgrade, there'll be another factor of 10 data that will be collected. And that just opens up then a completely new ball game in terms of the statistical accuracy of the measurements that can be made and the sensitivity and the reach for new physics that the experiments, of course, will be eager to look for with that data sample.
I mean, yeah, go on, carry on, Tara.
I'm butting in because I'm getting really enthusiastic. But if I could pick up on a point that Tulika made. So we're looking for the unknown. I think maybe you've got the message that we have a good theory and it's fantastic and we're exploring it still with the Higgs sector, but there's so much more out there that we're trying to understand. And as Tulika said, one way to do this is to look for new stuff directly. The other way is to amass enormous amounts of data to look for the really faint traces of new things if they're very rare or very weakly interacting. And this is where high luminosity LHC is really going to come into its own. So we've started exploring the Higgs. The Higgs is rare. High luminosity LHC is going to allow us to extend those investigations really beyond the particles we've been able to study so far to making our first observations really of how the Higgs interacts with lighter particles such as the muon and how the Higgs interacts with itself. We expect to see that, or we hope to see that with a full high luminosity LHC data set. And who knows what's out there? There's a whole, in my experiment, there's a whole program of investigations where we look for the indirect effects of new particles. And we're expecting orders of magnitude increase in our sensitivity. And so we're going into it thinking this is a complete exploratory discovery machine, and really looking forward to seeing what it's going to show us.
And part of the high luminosity LHC also involves replacing quite a considerable chunk of the actual LHC accelerator, isn't it? As I understand, it's like a kilometer, changing in terms of superconducting magnets. And maybe could someone just kind of mention briefly what that actually involves, the upgrade?
Maybe I could comment briefly, Michael. So of course the machine, the accelerator, is 27 kilometers long, and so I think it's fair to say that 90% of it is not going to be affected by the upgrade. But one of the most critical aspects of the upgrade is to replace the magnets in the final focus systems of the two large experiments, ATLAS and CMS. And so those are the magnets that take these incoming beams and then focus them down to very, very small sizes of the order of 10 microns in cross-sectional dimensions. These beams are when they cross one another. So the magnets need to focus those beams, and the more tightly they can focus the beams, then obviously the higher is the density of particles at the collision point, and therefore the higher is the probability that something interesting will happen. So the upgrade, a large part of that upgrade is indeed, it's to put in these brand new state-of-the-art superconducting focusing magnets based upon a new technology around niobium-3 tin as a special superconducting material. There will be tens of thousands of amps flowing in the coils of this novel material that will then create the magnetic field that will focus the protons down to these super tiny sizes and really give you, sort of needle upon needle like collisions of the beams of protons, and it's that will give you this much improved luminosity that will give you the 10 times data sample that we just talked about.
Right. And I'm going to slightly play devil's advocate a little bit here. Of course, when the LHC turned on, many people were expecting, that it would discover a slew of new particles, in particular kind of supersymmetric particles that were predicted by various kind of SUSY theories. Of course, that kind of hasn't happened. So is there a sense maybe that some of the science that has come out of the LHC is disappointing in terms of not discovering new particles?
Not at all. I don't think I can shout that loudly enough. The LHC has just been absolutely wonderful. We mentioned the Higgs. The Higgs is absolutely massive. I mean, it's such a huge step forward in really completing our picture and understanding of the standard model, providing, of course, it is a standard model Higgs. But before the LHC, we had no way of accessing this. And there's so much more that we've learned aside from the Higgs as well. Understanding the behavior of the particles that we know about in much greater detail, making the first discovery of matter and antimatter differences, of a different type of fundamental particle, the charm quark. There are just so many things. So at least from my point of view, it's been an absolutely huge, illuminating and wonderful success.
If I may just add to that, I completely agree with Tara, and I would say what we've also seen is the cleverness of the people along the way, that everybody is now trying to look for new physics in so many new different ways. And the fact that we had a measurement of the W mass with the precision that is the same as other previous experiments at a hadron machine, which is so complicated. We've been doing analyses that people that thought we wouldn't be able to do in the sort of the dirty environment of a proton collider. And so the fact that we've been able to do that, we've really opened up new ways of doing these searches. And there are theories out there, for example, which predict that the exotic physics might lie in particles which have unusual characteristics, meaning, for example, they are somewhat long-lived. They live a little bit longer than other particles, and then their final state signatures would look very different from the standard model particles. However, your detector and then your sort of reconstruction algorithms need to know how to look for these particles. And so we've been redesigning our strategies and our analyses so as to open up ways of looking for particles that maybe people haven't thought about before. And so that is also, I think, a big deal that we will be able to take advantage of at the HLLHC.
And the high carry on.
Sorry, Mike, if I may just come back and at you on that one. It's a bit hard ahead of time to predict when Nobel Prize winning discoveries are going to happen. Yeah. But I think it's true to say that the field has never been better placed than it is today through the Large Hadron Collider to make, the next Nobel Prize winning discovery in particle physics. We don't know what it will be. We don't know when it will come. But, 10 years from now, we might be talking about the discovery of dark matter particles at high luminosity LHC. Right? Let's hope so. But if we could predict it, we wouldn't need to do the experiment.
Great. I mean, just in terms of the high luminosity, just to end on that. So it's set to come online. I think construction is kind of ongoing at the moment, and it's set to come online at the end of the decade, I think. And then it's going to operate for around 10 years or so, around about that time, I think.
Yeah, so the present schedule has a shutdown of the LHC for roughly 3 to 4 years, and then the high luminosity upgrade will be installed during that time, and will come back on towards the end of the present decade. And I think the present CERN schedule has high lumi running until the end of 2041. So there's another 10 years plus of running with this super upgraded collider. And so, who knows what exciting discoveries are going to be made then.
You did mention the cost, Michael. So you mentioned the £1 billion cost, but the time scale is huge. So this is also what you have to bear in mind. And it's an investment for a considerable part of the future in terms of scientific exploitation. It's also an investment in terms of what comes out as spin-outs, in terms of the technology that's being developed. Phil mentioned those enormous currents that have to be carried. Superconducting power lines have to be developed to be able to do it. Those superconducting power lines are going to have great applications in, in grids to support the green economy. So, this is all an investment everywhere, not just for particle physics.
Excellent. Well, I'm slightly conscious of time though, so should we move on to the next section, which is kind of looking a little bit to the future, so actually beyond 2040, which is still quite a long time away, and that's really looking at kind of what will come beyond the high luminosity LHC. Of course, designing these huge particle colliders is a decade-long task. The LHC, after all, that was first mooted in the 1980s, I believe, but then switched on in 2008. So from what I gather then, particle physicists are clear on one thing, and that's the next particle collider should be a Higgs factory. So maybe someone could explain a little bit about what a Higgs factory is, and in particular actually why the LHC can't be or isn't a Higgs factory. Who wants to have a go at that one? Tulika or Tara, do you want to have a go at Phil?
I can start. Well, the Higgs factory, as the name says, is a machine that's really designed to study the properties of the Higgs. And yes, you could say that the LHC already is as a Higgs factory. However, what we do know is even at the end of the high luminosity LHC, there will be certain things we won't be able to do at the LHC, and that's for several reasons. But one of them is that this is a proton machine, so that means a proton is a composite object. It's made of other quarks and gluons, and when you're colliding protons, you end up with a rather messy environment. In comparison, you could have, for example, a lepton collider. So colliding electrons and positrons is something we've done successfully before. And now you know exactly what energy is going into that collision because these are fundamental particles, and the environment that happens after the collision is relatively clean. So you could have an E+ E- collider, which would then be able to create at the right energy enough Higgs bosons such that you can measure the properties of the Higgs, but in a very super clean environment. And this allows you to make certain measurements which will not be possible at the LHC, or to get to better precision. So they are what we call 3 generations of quarks and leptons in the standard model. The LHC can, say very good things about, for example, the 3rd generation, the top quark and the bottom quark, and its interactions with the Higgs. But if we start looking at the other generations, which involve the muon, the charm, the up quark and down quark, the LHC, while already doing pretty good, for example, for muons, will not be able to say definitive things about the 1st generation or perhaps the charm quark. So this is where the Higgs factory, an E+ E- collider, comes in and can really pin down what these sort of couplings are. And not just that, there could be sort of more exotic decays of the Higgs, etc., which also, again, the large sort of data sets that a Higgs factory could collect will really help to pin down if they are more exotic properties of the Higgs boson that we know of today. Maybe I'll pause here because others, I'm sure, will be wanting to jump in as well.
Yeah, maybe I could. No, go ahead, Tara, please.
Oh, we're so polite. Okay, I'll take a short amount of time and then over to you, Phil. So just to follow up on what Tulika is saying, I mean, it's one enormous step forward to make a discovery. But to really understand something, to really understand the implications for our understanding of the universe, you have to move beyond that. You have to really look at it in detail. So to just give you one example of one of the things that Tulika was saying, how much the Higgs couples to the electron. Now, there's no way on Earth we will ever find that out with LHC. It's just too difficult to measure, too rare a process to measure. But with a Higgs factory, an electron-positron collider of some description, then it does become a possibility. And this is important, not because it's stamp collecting, not because it's just something we've not seen, but because understanding why the mass of the electron has the mass it has, which the Higgs boson is responsible for, is of huge importance to our understanding of the size of atoms, chemistry, materials. It's a really fundamental property that these types of factories will help us understand the physical explanation behind. So that's the level of fundamental understanding that these machines are going to let us move towards. Sorry, Phil, go ahead.
No, not at all, Tara. I just wanted to expand on the advantage of electron-positron collisions that Tulika pointed to. So with proton-proton collisions at the Large Hadron Collider, one issue is that you don't know a priori which bit of one proton is going to hit which bit of the other proton, and you don't know how much energy and momentum are being carried by the two pieces of subatomic matter that actually collide. And that's not a problem for many analyses, but in electron-positron collisions, when the electrons and positrons meet and annihilate, you get back all of the energy carried, and so you know exactly what the energy is, and you also know what the total momentum is because it's actually zero. And so in the jargon, you have complete control over the kinematics of these collision events, event by event. And so if you had, for example, new particles produced that decayed invisibly, so decayed in ways that we couldn't actually see, you would still know that you were detecting processes like that because you would be able to measure the missing energy. You'd measure what you could see, you knew exactly what went in, and so from the fact that there was some missing energy, you could still make a discovery, even for exotic particles decaying to invisible things that you don't see directly. So it's a really very powerful technique. And I just wanted to make one further point, if I may. Although we often call it this machine the Higgs boson factory, an electron-positron collider of this type, it has far more uses beyond making Higgs bosons, as important as that is. So if you were to run it at higher energies, for example, you could make pairs of top quarks and anti-top quarks. Right. And we desperately want to understand the top quark. It's a fundamental particle, but it's 150 times heavier than a proton, and so that's a little bit strange. And so it's the heaviest fundamental particle that we are aware of, and we desperately want to understand it. And you could also run at lower energies, below the energy needed to produce Higgs bosons. And for example, you could look again at producing Z bosons. Now that was already done, of course, at LEP and SLC at earlier colliders, but the number of such events that you might create is in the range between 100 and 100,000 times what we were able to produce at LEP and SLC. And so that would open up a whole new ball game of precision measurements, really picking apart the Z boson and getting sensitivity to new physics indirectly, as Tara mentioned earlier, by making super precise measurements using lots of Z bosons. So it's really more than a Higgs factory, although we tend to give it the label of a Higgs factory. Some people say it's the Higgs and electroweak boson factory, but that doesn't roll off the tongue in the same way.
A bit more of a mouthful, that one, isn't it? But actually, didn't we actually already have a design for a Higgs factory then? I mean, I'm thinking in the form of the International Linear Collider. So I actually remember first writing about this back in 2008, and then a few years later, I think a full design for the ILC, as it's known, came out. So what was behind that switch then from circular colliders, which we've kind of had, or we still have at the moment, to this kind of more linear design?
Well, maybe I can start with that one. So let me just emphasize that there are two main designs of future E+ and minus colliders on the table today. There are circular ones and there are linear ones. So the circular ones are still very much there on the table. But the motivation for linear colliders is simple in a way, because the problem of sending charged particles round and round in a circle is that if they're electrons, if they're light particles such as electrons and positrons, then they radiate photons. So as fast as you try to get them to go to higher energies, they are radiating that energy away in the form of what we call synchrotron radiation. And that is a particular problem for very light particles, such as electrons and positrons. Protons are much heavier. They're 2,000 times heavier than electrons. And it turns out that the amount of power radiated in the form of synchrotron radiation goes inversely, like the fourth power of the mass of the particle. So if you had a proton collider of the same radius as an electron collider, it would be radiating 1/2000 to the 4 times less energy away in the form of synchrotron radiation. So even for the Large Hadron Collider, it's really not much of a problem. You can just about see the effects of synchrotron radiation, but they're very, very small. But for electrons, they're really very serious. And so I think it was felt, you know, back in the late 1990s, we had the Large Electron Positron Collider, 27 kilometers circumference, that got up to energies of about 200 GeV for collisions in the center of mass. And it was felt that that was probably the end of the road for circular electron-positron colliders because of the limitations of synchrotron radiation. So at LEP, 18 megawatts of synchrotron radiation was being produced, yeah, and so that required roughly 50 megawatts from the electrical grid to keep the electrons and positrons on axis, and they were radiating 18 megawatts away in the form of synchrotron power. And so people thought that, you know, to go higher in energies would be really prohibitive. But in fact, it was the discovery that the Higgs mass is relatively light. It's 125 GeV. Beforehand, it could have been anywhere up to 1000 GeV within the sort of allowed range, but it's come in rather light. And that means that an electron-positron collider to make Higgs bosons could have a center of mass energy of about 250 GeV, and that's only 25% higher energy than we had at LEP. So in fact, circular electron-positron colliders are very much back in vogue for the simple reason that nature has been very kind, and the Higgs is light. But to sort of answer your question, linear colliders don't have this problem of synchrotron radiation. And so if you really want to go to much higher energies, let's say well above 250 GeV in electron-positron collisions, then it becomes prohibitively difficult with a circular collider because of synchrotron radiation. And so that then motivates linear colliders, eliminate the synchrotron radiation. And in principle, you could build such colliders to go to 500, 1000, maybe even several thousand GeV in the collision energy. I'll stop there.
Tara, do you want to add anything, or?
Just maybe to say that there's always a trade-off in what you get between collider type, and Phil's absolutely right. If you want to go up in energy for an electron-positron collider and you have an accelerator of a fixed size, then if you want to exceed that, you have to look at a different solution. Now, the drawback, if I can say it, and I invite Phil to come back on this one, the drawback with a linear collider is that you don't recirculate your beams in the same way as you do in a circular collider. You have shots. So it's difficult to reach the same intensity of data, the same volume of data in a linear collider. So that's one difference between the technologies, although you can compensate because linear colliders can polarize their beams, and that can help reduce backgrounds for certain processes that you might be interested in, and that in turn enables you to reach a precision with less data than you would get otherwise. So depending on what you want to do, it turns out that actually both of the solutions are really competitive with each other, and that's why they're both on the table at the moment, and both still under consideration.
Yeah, I'd like to emphasize that, Tara. I know that I appreciate that this is not true of physics world, but journalists often like to have disputes among their panel members, right, and big arguments. I would say that there is no argument that an E plus E minus collider to serve as a Higgs boson, etc. factory is the obvious next step for the field. And then you can debate the relative merits of, well, should it be a linear machine or should it be a circular machine? And it's a little bit like, if I can take an automobile analogy, of arguing about the merits of a Rolls-Royce versus a Bentley. They are both absolutely superb, amazing options, and some have got bells and whistles over here and others have got bells and whistles over there, but you're really, you know, arguing about some fine details. But I think we all agree that an E+ E- machine is where we want to go. And then, you know, if you really want very high luminosities at lower energies, you might favor a circular machine. If you feel you need to go to higher center of mass energies, that's more difficult with a circular machine, and you might favor a linear machine. So that's where these debates then come in about, you know, what are your more detailed preferences for a program of such a machine. But I don't think there's any dispute that is what we should go for the field next.
I completely agree. Yeah, I completely agree with this point. And so that's why I think for me, I just hope that the world has an E+ E- machine, a Higgs factory sometime, you know, coming after the HLLHC, because the physics we'll get out of it is just wonderful. The one small point I want to add to the comparison, since we talked about some comparisons, is in a linear machine, typically you have one experiment where the collision happens. Whereas in a circular machine, you can actually have use magnets to make the beams collide at several different points along the circle, as is the case, for example, for the LHC. And that has a very special meaning, because if you think about it, you know, the discovery of the Higgs, right? The fact that two independent experiments discovered it using, you know, the data set that they collect, there is just a different kind of belief people have with respect to if it was just one experiment. I mean, it can still be done. You're just going to have to, you know, really prove yourself, you know, beyond any kind of reasonable doubt that it is just that one experiment that saw it. But that's another small difference between the two.
Can I come back on that? Even that is not strictly correct. So there is no reason that you can't have two experiments at a linear collider. Indeed, in the International Linear Collider design that Michael referred to, there were two interaction points and two detectors, and one of them at some point was eliminated in order to reduce cost. So the price you pay for having two detectors at a linear machine is that you have to share the luminosity between the two. So each would get notionally half of the data, but you can still have two. Half the time you send the beam to that one and half the time you send the beam to that one. But there's no free lunch. You have to share the luminosity between the two. So that point is often used as an argument against a linear collider. Well, there's only one detector, but it's a funny old world, isn't it? Because there's only one, you know, Hubble Space Telescope, but you don't hear people dissing the results from the Hubble Space Telescope because there's only one.
I agree completely, Phil. That is a very nice analogy.
I mean, in terms of the International Linear Collider, then, I mean, of course, I think Japan was primed to kind of host that particular facility, but it seems like it's that's kind of that process of kind of potentially hosting that has kind of dragged on quite some time. I mean, do you think has that dragged on too long, basically, that it might now never go ahead?
Again, since I've been intimately involved, maybe I can tackle that one first. So yes, I spent many years of my life contributing to the International Linear Collider, and the technical design report, the blueprint for that accelerator, was delivered in 2013. And here we are 11 years later, and I'm sorry to say that the International Linear Collider is no closer to actually being built today than it was in 2013. Now, to be fair to our Japanese colleagues, it was the Japanese high energy physics community that made a big push that Japan might host the International Linear Collider. It has never been a position of the Japanese government that they have agreed to that, and moreover that they would agree to pay a large fraction of the cost. So that's where the sticking point has been. I think, again, I don't want to be unfair to our Japanese colleagues, but I think the community has yet to convince the Japanese government that this is an investment that it should make, and the Japanese government has yet to come reach out to international partners to discuss possible contributions towards hosting such a machine in Japan. So it's sort of got stuck in the political sidelines. since we're all friends, I will just mention that there's a perfectly wonderful site for the International Linear Collider, only about 500 miles from where I'm sitting in Oxford, and it's called CERN in Geneva. So I think if, for whatever reason, the project at the moment, the Future Circular Collider, which is being very heavily promoted by CERN, if for whatever reason that turned out not to be a viable project, there is no reason why a project such as ILC could not be hosted at CERN at some point. But that's not where we are in the thinking today. But it could certainly be hosted other than Japan, somewhere other than Japan. It could be hosted in the United States, right? In principle, there's no reason. But obviously, the politics behind how you implement and host and pay for such a large project then starts to get in the way of the discussion.
Okay. I mean, yes, CERN has also another linear collider plan, or it did have one, which was a compact linear collider, wasn't it? And it seems now CERN then has basically turned to another design, which is the Future Circular Collider, which you mentioned before, which would be this huge 91-kilometer circumference collider, which would come in at quite an eye-watering costs of about £12 billion, I think. So it's a bit of a terrible pun, but it seems like we've come full circle then back to circular colliders. So what's behind then? I mean, I think we've touched upon this a little bit, but what's behind that decision then to come back to the circular design?
Well, again, maybe I can just start and then I'll shut up because I don't want to monopolize the discussion. I think it's the fact that so let's suppose the Higgs boson had turned out to be very heavy, and it turned out that you needed an electron-positron collider with a center of mass energy of 1000 GeV in order to make Higgs bosons. You could not do that with a circular collider. The fact is the Higgs boson is surprisingly light, and with a 250 GeV E plus E minus collider, you can have a fantastic Higgs factory, and that means that a circular option is really back on the table. Now, the synchrotron radiation still forces you to a much larger circumference facility than we had at LEP. So the LEP energy was 200 GeV, 27 kilometers. The proposal for FCCEE is 91 kilometer circumference machine, and that gets you to 25% more energy in a relatively straightforward way than one had at LEP. So you beat the synchrotron radiation by making the circumference of the machine so much larger, so that if you like, the electrons don't quite notice that they're being bent so strongly because the circle has been made bigger, and therefore you reduce the problem of synchrotron radiation. So it's fundamentally the fact that a lower energy E plus E minus collider than we might have guessed 20 years ago is now on the table. And so FCCEE is a really wonderful design for a circular E plus E minus Higgs factory. But you're quite right, ILC is still there on the table as a possibility. And at CERN, another linear collider, CLIC, the compact linear collider, is something that CERN has invested in over many, many years. But it's presently also, if you like, on the sidelines as a possible plan B, should the FCC, Future Circular Collider, not prove to be viable for whatever reason.
I think there's a oh, sorry, go ahead.
I was going to just jump in and say that in my view, I think the circular option FCCEE has become popular is because it's seen as a stepping stone towards the larger machine, the Hadron machine, 100 TeV Hadron machine that would use the same infrastructure, the same large tunnel, and that would then be the ultimate discovery machine, which can really pin down the Higgs interaction with itself and really have this large energy jump that would allow you to discover particles if they are indeed, 30, 40 TeV scale, for example.
I want to underline this. I don't know how practical it would be for us to just build an enormous collider for the E plus E minus stage, full stop. I think it's within a view to the future, and it is a really long-term future. This program will go on until almost the end of the century. It's going to be a real discovery complex. It really will have the energies to take our understanding way beyond where we can go to now. And that's the attraction of this. And if I can just come back, you mentioned the cost. Just some context, because it's always helpful to have context. So this is going to be a huge machine. If you're in the UK, for context, it's going to be about half the length of the M25, so pretty massive. And the cost is about 1.5 times that of the Channel Tunnel, because it is really substantial infrastructure. But it's about the cost level of really substantial infrastructure. And bearing in mind it's for a facility that's going to be spread for the remainder of the century. You just have to take that longevity in mind, and remember that it's not being paid for in a one-off type arrangement, that it's being covered by the money from the member states and their annual subscription, and associate states with their subscription to it, and so forth, and managed over the lifetime of the project. So I just wanted to set that slightly longer time scale against the cost.
So remember, Michael, the annual budget of CERN at the moment is about 1.3 billion Swiss francs, and that's paid for by the 24 member states. And so, you know, it's an interesting exercise to think, what can you afford on that budget? And so in the present imagined funding model for the future circular collider, maybe it's possible to pay for roughly 2/3 of it out of the existing CERN budget subscription line. But then one would certainly need to try to secure additional contributions from other parts of the world beyond the normal CERN budget.
Mm-hmm. I mean, just to bring Tulika in, I mean, from a US perspective, then you were involved in this particle physics project prioritization panel, a bit of a tongue twister, which is more easier known as the P5 panel, that every decade comes together to kind of set the course of US particle physics. So one of the recommendations in that was the construction of a Higgs factory, but it didn't come down in particular on one design, did it? So what's kind of the US perspective on the Higgs factory?
Yeah, sure. So I think what we established as part of, there was a community process, and then the P5 comes in to really come up with a strategic plan that also takes into account budgetary considerations. And as a result of that discussion, we concluded that where the science was concerned, clearly after the HLLHC, a Higgs factory is what the US was most interested in. It was clear from the US budget, because we have a large neutrino experiment being designed in the US, that we could not afford building a Higgs factory in the US. So this would therefore be something that was built elsewhere in the world. We felt that whether it's an ILC or an FCCE, the science satisfies our needs, because what we will get out of these experiments will be very, very similar. So we are therefore very much in favor of a Higgs factory after the high luminosity LHC as sort of the more sort of medium term like project, with the idea that this would then of course be followed by this discovery machine that comes later.
Right. In terms of the technologies then for the FCC, HH, and maybe even the EE as well, as I understand, kind of new technologies will be required to build this kind of new huge Hadron Collider that could reach 100 TeV. Don't know if anyone could kind of briefly just talk about that.
So I mean, the big issue for the Hadron machine is the magnets, because you have to build super strong bending magnets to keep the protons going around on their 91 kilometer circumference trajectory. And so the magnets in the Large Hadron Collider, the dipole magnets, have a strength of roughly 8 Tesla. You know, the Tesla's a funny unit because 8 Tesla doesn't sound very much. That's 100,000 times stronger than the Earth's magnetic field. Okay, so these are absolutely, huge strength dipole magnets, 8 Tesla at the Large Hadron Collider. And so thinking about the magnets that you would need for this future circular Hadron Collider, people are looking in the range of 16 to 20 Tesla. And that is really pushing the bounds of magnet technology. So I think it's absolutely true that today, nobody really knows how to build such magnets. There's a huge effort going on around the world to do the R&D. People are constantly making progress. I heard at CERN only 2 or 3 days ago about 13 Tesla magnets that are being developed already in the context of high Lumi LHC. So there's tremendous progress being made, but that is the big technological uncertainty at this moment. We really don't know how to build the magnets. But on the other hand, if one follows this model of the electron-positron collider first, followed by the hadron-hadron machine, then we still have several decades in which to master the magnet technology that we would need for the hadron machine.
Yeah. Yeah, I'm just conscious a little bit about time. We've just got a few minutes left. Tulika, I just wanted to ask you one thing about in terms of what came out of the P5 report, which was the kind of this development of a muon collider. I think the P5 report called it a muon shot, kind of in reference to the Apollo moon program. So maybe you could describe a little bit about that, then what that is, possible timeframes if it ever happened.
Sure. So I think we talked about, how an electron machine is wonderful because it's a fundamental particle. You know exactly what energy is going in, clean collisions. However, it has the challenge that it's relatively light, so there is a lot of the synchrotron radiation. So then you start to think about, can we get a fundamental elementary particle that is more massive, such that we still enjoy the wonderful properties of fundamental particle interaction? However, if it's more massive, then there's going to be less radiation. And therefore, you come up with the heavier sort of elementary particle, the muon, which exactly has those properties. So with a muon collider, you could get the best of both worlds in a way, that of an electron machine as well as a proton machine. However, the challenge is the muon is very unstable. It decays very rapidly. And so you have to have this beam of muons that you're going to get, and you're going to have to cool them, focus them, and then make them collide before the muon decays. And so this is where, again, there is a big technical challenge in here, and we don't know yet if we can do this. However, there have been some preliminary studies related to cooling a muon beam, which seem to indicate that perhaps there is no showstopper. However, a lot of R&D that will have to be done in the next several years. So we're looking at the earliest, I say, a time scale of 20 years when we will get to that point via demonstrations and R&D en route to give a go-ahead kind of whether or not there could be a muon collider. But so best case scenario, I would say 1950s, which would also fit within the US budgetary situation, that we would be done sending money to our big neutrino project, and therefore perhaps we can start in a global way, because this has to be a big global collaborative effort. Then think about hosting a muon collider in the US.
And this is something that could fit into existing facility like Fermilab, for example, in terms of the Tevatron tunnel. It could, that kind of scale of around, is that correct? That kind of rough scale?
Fermilab campus. So the nice thing about the muon collider is, again, you do not need that huge, massive 90-kilometer tunnel. And again, because of that reason, you can actually fit it. And so when people did the studies to figure out where they could fit a potential muon collider, when they emerged with the conclusion that, it could actually fit on the existing Fermilab campus, that just was one of those amazing moments that you realize, oh, wow, there is this reality that there is a potential site if everything were to work out.
Great, well, perfect. Well, I think that's almost the end then. So certainly a lot to think about in terms of all these interesting proposals for what might come next in high energy physics. But I guess, like most things, it might come down to one thing, which is actually money in the end. But in any case, it's going to be an exciting few decades ahead. So thank you again, Phil, Tara and Tulika, for a fascinating discussion, and over to you, Mateen, to close.
Yeah, thanks very much, Michael, and the speakers. That's all we have time for today. And it's incredible to think, as Tara mentioned, that we're talking about centuries, huge timescales. but hopefully lots of exciting things to come. So thank you very much to all our speakers and to our partner Reports on Progress in Physics. And of course, thank you all of you for attending. I do want to mention the next Physics World Live, which will be on the 21st of November, and something very practical, the future of battery technology. So thank you for being here on our second Physics World Live, and I hope you will join us for the next one. Thank you very much, and goodbye.